Bien. Vale. Todo bien. Vale. Okay, so welcome to this first session of the 2021-22 session of the Hanneke Coffee Talks. Today, in this Severo Ochoa Coffee Talk, we have with us Hanneke Heida, accepting, who obtained her bachelor and master in science in earth sciences at Utrecht University. And now she's currently working as a PhD candidate at the Geosciences in Geosciences Barcelona, at the CSIC, under the supervision of, I suppose, Dr. Daniel García Castellanos and Dr. Yvonne Jiménez Moon. So thank you, Hanneke, for participating, and the floor is yours. Thank you.
All right. One moment. So you can see my screen?
Yes, yes.
Perfect. Okay. Then I'll start. So hi, good afternoon, everybody. So as Alex said, I am a PhD student working at the Geosciences Barcelona Institute, working on my PhD related to the Messinian Salinity Crisis. So first of all, I'd like to thank Alex and Lucia very much for organizing and giving me the opportunity to share my work with you. So this might be, I realize that my work might be quite far out of your own field. So what I would like to do during this talk is to give a kind of general overview of what the Messinian Salinity Crisis was and what its effects were on the Mediterranean Sea. As this was a very, very big environmental and hydrological crisis that occurred between 5 and 6 million years ago, and that left a huge deposit of rock salt that is currently buried in the surface, underneath the surface of the Mediterranean Sea. And I would like to give you a little bit of an historical perspective also on why this has remained such a controversy in the geosciences community for a long time, and how my own work in my PhD is aiming to help resolve some of these controversies. So what I am doing is using numerical modeling to make topographic reconstructions, and later on you will see how these are implemented in the broader research. So my PhD is part of the Salt Giant European Training Network, which is funded within the Horizon 2020 program from the European Commission. And we are a group of 15 early stage researchers related to a bunch of different academic and private sector organizations, both inside and outside of the European Union. And what we are trying to do as a group is really understand the Mediterranean salt giants and the Messinian salinity crisis in a very broad sense. So there are geoscientists like me that are working really on the formation and the evolution of the salt giants. But we also have, for example, people working on the economic impact of hydrocarbon reserves related to the salt giants. There's people working on the history of science and the development of ocean sciences in Europe. And we even have biologists that are looking into how microbial life is able to survive inside salt crystals as a possible analogy to life on Mars. So a very, very wide range of different subjects that come together within this organization. And of course, besides our own research, the training network is also aimed at providing training both to people within and outside of this consortium. And for example, here we all are during a field trip in the south of Spain, doing our best impression of a gypsum cone that you can see behind us. So what I would like to start talking about today is the idea of what a salt giant is and how they form, and why the Messinian salinity crisis and the Mediterranean salt giant is so interesting. So normally salt giants are able to form in two distinct ways. One is related to the birth of an oceanic basin. So when you start to rift apart a continent and a basin forms, and it slowly gets a kind of tenuous connection to the global ocean. Then water is able to flow in, but as the connection is not very stable yet, the first amount of water will evaporate and leave a large salt deposit. And examples of such type of salt giants can be found, for example, around the edge of the Atlantic Ocean. And they are formed in the Mesozoic time. So those are mostly between 65 and 250 million years ago. So they are quite old, and they are related to just the opening of the Atlantic here. And then another possible way to form a salt giant is the opposite, related to the closure of an oceanic basin. So as an ocean is subducting, it will at some point be the victim of continental collision, and it will be trapped. You will have a remnant of an oceanic basin trapped between continental plates. And at that point, of course, also its connection to the global ocean will be disrupted. And most of the salt giants that we see that have such a nature are very, very old, related to ancient oceans. And by very old, I mean like more than 250 million years old. And we find them in the interior of continents nowadays. But the Mediterranean salt giant is actually also an example of such an event, because the Mediterranean Sea is at this moment being trapped between Africa and the Eurasian continents. So it is a little bit unique in a sense, because it's much, much, much younger than other salt giants of this type, being only about 5 million years old. So it gives us really an opportunity to see how these salt giants are formed and to look at the effects without the very, very long geological history later altering the effects of this event. And of course, it's quite interesting because in the modern day, we have normal marine conditions in the Mediterranean. So right now, there is just normal marine waters, and there is no formation of salts going on at the bottom of the Mediterranean. So how is it possible that in the past we did have this period of salt formation and these kilometer-thick salts that are now found in the deep basin? So first, very briefly, I'd like to just say what is going on exactly when you're forming evaporites or rock salts. Now, if we take 1 kilometer of seawater and we would evaporate this, then as the salinity starts to increase due to the loss of the fresh water by evaporation, minerals start to precipitate from the water as they are no longer soluble enough to remain in solution. And if you entirely evaporate 1 kilometer of water, you will get about 17 meters of minerals forming, where first you get the least soluble minerals coming out of the water column to form gypsum. Then there is a thick layer of halite or rock salt. And then in the very last few percents of water evaporation, you start to precipitate the least soluble salts, which are potassium and magnesium salts. But as you can see from here, if you would evaporate the Mediterranean basin today, you would only get between 25 and 50 meters of rock salt forming. And what we see in the salt deposits that we actually observe is that they have thickness of kilometers in some cases. So there must be something more going on than just the disconnection and evaporation of the water. So normally, as a geoscientist, we have a lot of different tools to our disposal. For example, if you go into the field, you can take samples and you can do chemical, biological, physical analysis on everything you find. But it becomes a little bit more complicated when we are studying things that are stored in the bottom of an ocean basin, buried between kilometers maybe of sediments and water. So there are 2 main types of data that I will be discussing today and that we use in our research. And that are seismic data and drilling boreholes. So seismic data is basically doing an echography of the seafloor by sending out a research vessel that has a seismic source that creates a wave. And this wave then travels through water and the different layers of sediments or rocks in the seafloor. And every time there is a change in the composition of these layers, part of the energy is reflected and recorded back on the ship by a receiver. So if you process all the arrival times of these different seismic waves, you can construct an image of all the different layers in the seafloor and also of structures that will show up, for example, as an incontinuity within these layers if you have the sediments being affected by faulting, for example, by tectonics. So this data is very important to understand how the subsurface looks like, but it doesn't give you a lot of information about the real composition of the rocks. So in contrast, a drilling expedition is a little bit more useful in the physical sense here, because you just send a ship and it's able to send a drill pipe down to the seafloor and drill down to kilometers below the seafloor in some cases, and retrieve physical samples of the sediments or the rocks that you were studying. And this gives you the advantage that you can measure, for example, the chemical composition of these sediments, and also take a look at the microbial life that is living in the sea water column and below the seafloor. And this gives you a lot of information about the environmental conditions that were present in the basin at the moment that the sediments were formed. So a combination of these kind of data can usually give you quite a lot of information about what is going on in a basin. Now, when it comes to the Mediterranean there and to the study of salt giants in general, there are a few big challenges to gathering data that we would like to use to decipher the big questions about this event. And some of them are actually related to the mechanical properties of rock salt itself. So for example, rock salt has a very low porosity and permeability, which incentivizes the creation of overpressure underneath the salt. And this is a risk during drilling, as you can create a blowout if you don't have a pressure control at the entry point of your drill pipe. So a normal sediment will contain of grains of different minerals, and they will have pore space around them and permeability that allows the free movement of gases and fluids. But because salt is a chemical precipitate, it has a very, very low porosity, and these gases and fluids are not able to move through it. So if you have a layer of salt laying on top of sediments, then the pressure that can build up below that salt layer will cause a risk that is able to be mitigated by using special drill ships called riser drilling. But so far we have not had any riser drilling for scientific purposes in the Mediterranean that was able to penetrate the salt layer that we have there. So we don't really know what is beneath the salt in the deep Mediterranean. And even though this would give very key environmental clues to what was happening during the salinity crisis. Now, a second issue that we have is that salt behaves as a highly viscous fluid on geological timescales. So similar to ice, it's able to flow and move under pressure and to cause big migrations of masses over geological time. So for example, what you see here in the right top are salt domes that are being formed in the Mediterranean subbasin, which are caused because the salt has a lower density than the overlying sediments, and it starts to rise. It's able to rise actually kilometers through the overlying sediments. And in some cases, you even see these salt domes penetrating all the way to the seafloor. But this means that the salt no longer is in the same place that it was when it was deposited, and it no longer has its original thickness and volume. Well, especially thickness, the volume should remain constant. And this complicates the interpretation of seismic data and the interpretation of the situation under which this salt was deposited. And what you also see, for example, is a very cool example here in the Eastern Mediterranean. This is the Nile Delta, and what we see is that the pressure that is being created by the sediment deposition in the Nile Delta is pushing out the salt that was laying underneath it radially, and this salt flowing, you can actually see, is deforming the seafloor. So if you go on Google Earth, you can see this for yourself. But it's clear that if we want to know exactly what was going on during the Messinian crisis, we need to be able to more or less know where the salt originally came from. Now, a third issue is quite simple. It's the high seismic velocity of salts. So these sound waves are able to move through salts at very, very high rates compared to through normal rocks. And what this means is that because there is a very big contrast in the composition of salts and the overlying layer, a large amount of the energy when you are trying to make seismic lines will reflect off the top of the salt. And afterwards, remaining energy will be absorbed by the salt itself. And this is means that you can image the top of the salt very nicely, but the material that is buried underneath the salt is not very visible in seismic lines. So we can not reach it easily by seismic investigations or by drilling in the deep Mediterranean case, which has really been a problem in the resolution of some of the issues that we are facing with the Messinian Salinity Crisis. So what do we see in the Mediterranean, and what are the records that the salinity crisis really left? Now, there are 4 important factors that are taken into consideration when we are researching the Messinian salinity crisis. And that is the kilometer-thick halite deposits that we find in the deep basin, in the east, central, and western basins, which is in yellow here. And this is mostly constrained to the deep basins, but we do see some small patches in other areas, slightly shallower as well. And then on top of this halite, we have gypsum deposits. There is believed to also be gypsum underneath the halite in some places, and there is gypsum in the marginal basins, which are partially exposed onshore. But the part that is onshore only represents about 5% of the total evaporites. and they are not very representative. So what we know is that this gypsum was actually formed in water that was lower in salinity than when the halite was being deposited, and yet it is found on top. So there must be environmental changes going on in the Mediterranean, even within the salinity crisis. Now, the total volume of these salts reaches about 1 million cubic kilometers, which is huge. It represents about 5% of global ocean salinity. So it had a global impact for sure. And another thing that we see is that there is deep or strong erosion on the margins of the Mediterranean Sea and incision in river valleys. So normally a river will flow to its base level, which is the point where it flows out to sea. And you can imagine that it's not able to erode deeper than that base level. When you drop the water level, that means that the river is all of a sudden able to incise deeper into its own stream bed. And you can form a canyon that later, as the sea level rises again, gets filled in by marine sediments. And we see this, for example, in the Rhone and the Nile deltas. And what we know from stratigraphy, from materials on top and below the Messinian sediments, is that the total duration of the crisis was about 640,000 years, between 6 and 5.3 million years ago. And this is really quite short considering the amount of materials that were deposited in this time. So in order to understand how this could have happened and also why the Mediterranean isn't currently depositing salts, it's important to have a bit of an overview of how the Mediterranean works in this day and age. So what we see here is a cross-section, very schematic, through the Mediterranean Sea, where we have the Strait of Gibraltar here in the west, then the Western Mediterranean and the Eastern Mediterranean with, again, a kind of topographic divide in between. And the Mediterranean basin is an evaporative basin. Now, what does that mean? That means that the amount of water that is being lost to the atmosphere by evaporation is currently not being compensated by the inflow of river water and rain. So if there wasn't a connection to the Atlantic Ocean at the Strait of Gibraltar, the surface of the Mediterranean Sea would start falling by about half a meter per year due to evaporation. So the volume of water in the Mediterranean Sea needs to be compensated by the inflow of Atlantic marine waters in a top current at the Strait of Gibraltar. Now, as you can imagine, if we have water flowing in that contains salt, as it is marine water, and we have only fresh water evaporating, if there is no way to get rid of this excess salt, then the Mediterranean would slowly turn into a brine pool and start depositing salt, a little bit like we see in the Messinian case. So this excess salt is actually expelled from the Mediterranean by a saline deep outflow current in the Strait of Gibraltar that is being pushed by the density differences between salter and colder water and inflow water. So as long as you have an open connection to the open ocean, it is not very possible to get a big salinity gradient between the Atlantic and the Mediterranean, just because of the differences in density that would force such an outflow current to exist. But what you can imagine is that this entire Mediterranean system now becomes dependent on this very small connection that we have at Gibraltar, which is really only a few kilometers and a few hundred meters deep at its narrowest points. Now, this gives already a few clues to how the Messinian salinity crisis could have happened, and it also inspired people to imagine different scenarios for the Mediterranean even 2,000 years ago. So, for example, Pliny in his Historia Naturalis already wrote, "At the narrowest part of the straits, there are mountains placed to form barriers to the entrance on either side. Ibila in Africa and Calpe, which is Gibraltar Rock in Europe. The boundaries formerly of the labors of Hercules. Hence it is that the inhabitants have called them the columns of that god, and they have also believed that the way they were dug through by him, upon which the sea, which was before excluded, gained admission, and so changed the face of nature." So even 2,000 years ago, without any knowledge about the salt that is present in the Mediterranean basin, this Strait of Gibraltar and the strong currents that we see there already inspired people to get this kind of mythological idea about how the Mediterranean could have formed. And they imagined actually this empty basin being filled by an inflow from the Atlantic Ocean. And actually, this same narrow connection also inspired quite some interesting plans. related to geoengineering. So, for example, in the early 20th century, the Hermann Sorgel, a German architect, he envisaged this giant project where he wanted to propose to build dams at the narrowest point in the Mediterranean Sea. And the objective here was to unify Europe and Africa by infrastructure, by energy supply through giant hydroelectric dams, and to expose part of the Mediterranean seafloor by lowering the water level about 100 meters, and thereby creating huge new land that could be used to build new cities and to use for agriculture. And of course, nowadays we know a little bit better the kinds of environmental and climatic effects this would have on the Mediterranean Sea, probably causing a collapse of the entire Mediterranean ecosystem. But in this time, this was pretty seriously considered by people that saw this as a way to advance industrialization and world peace. And actually, even more recently, there have still been people that have proposed damming of the Strait of Gibraltar as a way to mitigate the effects of climate change. So, for example, there is this 1997 paper that proposed that we need the dam to prevent the cooling of the Northern Hemisphere. But the argument was being driven by the increased saline outflow at the Strait of Gibraltar and its impact on global ocean circulation. Or this even more recent 2015 paper where they suggest that actually a dam could be a cost-effective measure to control the water level in the Mediterranean region, where it could, for example, be combined with the out-pumping of saline water to prevent salinification, or perhaps that even the salinification of the Mediterranean Sea is an acceptable price to pay for maintaining the shorelines in this very populated area. So what is, in my opinion, a very cool thing is that the research that we are doing into the Messinian Salinity Crisis also gives us an idea of the impact that human interventions could be having on the Mediterranean system and how the Mediterranean could develop in the future. For example, human activity is already having big impacts. By example, the use of fresh water that formerly would flow into the Mediterranean, and by the effects of climate change that are changing precipitation patterns. So when we go back in time a little bit to the 1950s, we have the first formulation of this hypothesis of a salinity crisis. And this was based on the observation that you have these very similar types of evaporite deposits forming and found onshore all around the Mediterranean. So here we have examples from the Northern Apennines in Italy, the south of Spain, and also Sicily, where you see similar gypsum layers forming in these cyclical patterns. And this led to this idea that there might have been this pan-Mediterranean event that caused the salinification. But there wasn't yet this clear idea that this also affected the deep basin. So in the 1950s, we also have the first oceanographic explorations really going on in the Mediterranean. And from the seismic data that was being gathered, we see that there was this strong reflective layer, which was called the M reflector, that the seismic lines were not very clear underneath, and they were believed to be related to the opening of the Mediterranean basin. And the material that was buried underneath this reflector really wasn't known very well. And this changed when in 1970, the first scientific drilling expedition entered the Mediterranean in the context of the deep sea drilling project. And this expedition really was aimed at understanding the tectonic evolution of the Mediterranean basin, but they didn't expect to find evaporites. So you can imagine the surprise of the scientists on board when they are drilling through hundreds and hundreds of meters of completely normal marine sediments. And all of a sudden they hit a layer where you find pebbles that look like they have been deposited in a riverbed. And you find cracks in the muddy seafloor that looks like the mud that has been dried by the sun. And you also find fragments of gypsum that is an evaporative mineral that can only be formed in an evaporative basin and not in a deep marine basin like the Mediterranean. And eventually, on this drilling expedition, they managed to drill into the top of the salt layer in the deep basin. And really on the ship is where this theory of a desiccated Mediterranean was born and started to gain traction. And as the results of this cruise were being published, it also turned out that a Soviet scientist that was working on the construction of the Aswan Dam in Egypt found independent evidence that the Mediterranean might have been lower in the form of a riverbed that had been deeply incised at the Aswan Dam, which is hundreds of kilometers south of the current mouth of the Nile River. So what he finds there is that there is a riverbed that was incised for hundreds of meters and then filled with Pliocene marine sediments. So the Pliocene is the geological time after the Messinian. And in order for the marine sediments to have reached this far, there must have been a deep river channel incised all the way that was then invaded when the sea reached its normal water level again. But over the next 50 years, a lot of research has been done from a lot of different geoscientist perspectives. And this really has not been able to solve the main controversy, which is still around, was the Mediterranean desiccated? Was the sea level lowered substantially? Or was there always water in the Mediterranean? Did it simply salinify at some point? Because people that don't believe in the drawdown of the Mediterranean have alternative mechanisms for the formation of some of the things that we see. And also there is quite intriguing geochemical and biological evidence that suggests that actually there must have been a high water level in the later stages of the Messinian Salinity Crisis that allowed for the exchange of chemical and biological components between the deeper and the shallower basins. So this is one of the things that I hope to be able to answer with the research that I'm doing for my PhD. Because what we want to do is to look at the features that we have now that were formed by the Messinian Salinity Crisis in the Mediterranean. So these are both the erosion surfaces and the evaporates that we find. And we know their current depth, but something that we don't know is at which depth they were originally formed. And if we know the original topography of the basin, you will be able to hopefully say whether salt was formed only beneath a certain depth or at many different levels, whether there were connections between the different parts of the Mediterranean basins, or if some parts of the basin was isolated, and also how far and if it was a consistent water level that we must have had during the drawdown in order to form the erosional features that we see. So the answer to some of this question can hopefully be found in the paleotopographic reconstructions that we are using numerical modeling methods to obtain. So in making these paleotopographic reconstructions, our main method is called backstripping. And this is a technique that we use to determine the depth of a surface through time and the vertical motions that have been affecting its position since it was formed. So you want to constrain a number of different components of vertical motion that could have affected the basin. The most important one is flexural isostatic subsidence. And what this means is that if you have a crust and you apply a sediment load, for example, a big layer of evaporites, then part of the weight of that sediment will have to be compensated by buoyancy forces in the mantle. So the mantle will flow away and allow the crust to sink down in the position where you have this load applied, and to compensate for the weight of the material. And this is called isostasy. Now, under isostasy, we assume that the weight is completely compensated by buoyancy in the crust. But of course, or in the mantle, sorry. But of course, the Earth also has a rigid crust, which we can visualize as a thin elastic plate, and which has the capacity to support part of the loading strength. So when we treat the radiological components of the crust and we calculate how thick this theoretical elastic layer would be, we can calculate how much this would affect the isostatic subsidence that we expect to get after loading by, for example, the halite or the post-Messinian sediments. And this is called flexure. So another component of vertical motion is the compaction of the sediments that are being buried. So this is related to this pore space that I was talking about earlier. As you are burying sediments, they get pressurized and the pore space will start to decrease, which means that the thickness of the sediment layer that we see now in our seismic lines and in our cores will be slightly thinner than the thickness of that sediment layer while it was at the surface of the seafloor. So you want to compensate for this to know the original depth of that layer. Then the third component is the thermal subsidence of the Earth that is related to when you form a crust, it will be warm and buoyant, and then as it starts to cool down and age, it contracts and gets denser and it will start to sink. And this is something that happens to all ocean basins, and we can calculate based on the age and the extension of the basin. And then the last possible component of vertical motions could be tectonics, but I won't go into that here today. So there have been some previous backstripping studies done in the context of the Messinian Salinity Crisis. Here I'll highlight two of them that were done in plan form, so in 3D, where you can see over a surface what is going on. Here on the left, we have an example of a backstripping study done in the Ebro River Delta. And here there was a high resolution 3D seismic cube that allowed for the identification of different types of erosion surfaces and of a river channel incision. And the reconstructed topography there suggested a water level of about minus 1,300 meters. So that's quite interesting, as this is a first indication of how deep the water level could have been while these erosion surfaces were being formed. And then also we have here on the right a study that was conducted in the Po Plain and the Adriatic Basin, where the similar type of backstripping and topographic reconstruction suggests that the water level was about minus 800 meters, and that this part of the basin was actually isolated from the rest of the Mediterranean during the Messinian Salinity Crisis, and that partially explains where there is no salt found in this region. But these are results that are representative of the local conditions in those areas. And the aim of what we want to do in a paper that was recently accepted for publication, where we work together with co-workers in Montpellier and in Toulouse, is to take advantage of all the data that we have available in the Mediterranean or in the Western Mediterranean that was collected over the last few decades, and to do a very large-scale topographic reconstruction to see if we can find consistent estimates for the amount of water level drawdown that we needed to find the shorelines that we proposed during the Messinian. So the reason why this region is interesting is, first of all, that it has not been affected very strongly by tectonic activity since the Messinian. So we think that most of the markers that we find are still more or less in their original position. And also, this region really records a very wide range of depths, which means that we have the deep basin where we have the halides. Then we have a shallower region here between the Balearic Islands and Spain that does not have halite, but does contain the evaporites that we find on top, the gypsum. And this is bounded by erosional surfaces that we believe to have been formed by exposure to the air and by the incision of water flowing down from the rivers from the continents. And another interesting feature in this region is that we have a few patches of halides scattered at different depths around the Balearic promontory. And these can give us an idea of at what depth actually halite was being formed during the salinity crisis. So we perform our flexural isostatic reconstruction, going down back in time, step by step, removing the sediment units, the evaporite units, and imposing a certain water level drop to match the position of a shore where we believe the shorelines might have been that are related to the location of the evaporites. And we also calculate the isostatic effect of lowering the sea level. So when you remove a kilometer of water, actually you can expect the crust to come up by about 300 meters because of the loss of this load. And what we find is that we find two different shoreline levels, where one is about minus 1,500 meters related to the formation of erosion below the green upper gypsum evaporites here in the Valencia Basin. And then there is a second shoreline position that is slightly higher at about minus 1,100 meters related to the formation of the upper unit here, which we know must have been formed in water. So we use the limits of this green unit as an indication of a shoreline. And another interesting result from this study is actually that we find that these patches of salt that we find on the Balearic promontory were formed at a very wide range of depths, and they are not really clearly related in salt thickness to their formation depth. So what we see, for example, is that we have a very shallow basin here in the Corredor Basin, which is about 600 meters deep and has a thin salt unit. And then the Central Majorcan Depression here between Ibiza and Mallorca is formed relatively deeper and has a slightly thicker halite unit. But then the last mini basin that we looked at, which is the Formentera Basin here, is actually much thinner, but also formed way deeper than the other two basins. So there is not really a clear correlation. And it suggests that actually salt might have formed at a very, very wide range of depths, much shallower than it is generally preserved in this day. So this led us to propose two different models for possible deposition of halite that can explain why it is preserved in the places that we find it nowadays. So the first model says that we have evaporation and brine forming at the surface and halite forming at each depth in the basin, where all the slopes and shelves were basically covered in a halite layer that was subsequently dissolved or eroded as the water level fell. And the only places where halite is preserved is in locations where you have small topographic minima, where you cannot have the water that is eroding the salt layer leaving that small depression. So another alternative explanation could be actually that you get brine formation at the surface, which then sinks to the bottom and accumulates in topographic minima, which means that you only get salt forming in these locations, and that in open shelves, this dense water would just keep flowing down until it reaches topographic minima or a deep basin. And in this case, actually, after the drawdown, you would get a similar pattern of halite preservation. But we think that this scenario is less likely based on hydrological considerations. But yeah, these are roughly the type of explanations that we have for the halite occurrence that we have nowadays. And ideally, we want to compare these to different regions to see if this will be consistent between other parts of the Mediterranean as well. So currently, I'm working on a similar reconstruction going on in the Albadan Basin, which is here the westernmost part of the Mediterranean. And this region is more complex due to its tectonic situation, where it's being compressed between Africa and Iberia. But it's also very, very key, as this is where we have the Gibraltar Strait and the other oceanic corridors that were present before the Messinian. And reconstructing the topography here can really help us to understand how the Messinian Salinity Crisis might have started and ended. And another thing that we can do after we have a topographic reconstruction of the Mediterranean is actually to start thinking about what the effects would be of the water level drop in terms of the evolution of the surface. So we can use numerical modeling tools to also look at what happens in the Mediterranean rivers, where does erosion occur, and where are sediments deposited that are being eroded from the shelf and the original mainland. And we want to see if we can use these surface evolution models to constrain the duration, for example, of the drawdown and other properties such as the climatic variables that were present during the Messinian. But this is work for a later day. So I think I've been talking long enough now, and I'll leave you with this. So I would like to thank all of you very much. And I'd be happy to answer any questions if you have them.
Thank you, Hanneke, for their presentation. Really interesting and complete. Also a difficult topic. I can see it. But as you said, if any of you have any questions or comments or suggestions, you're free to say something. I was okay. Yes, okay.
Hi, Valentina.
I was curious about the last thing you were talking about, this surface evolution models. Do you know, I mean, any detail of how they work, or because with some of us, I think we are working on similar stuff in these numerical topics.
Yeah.
Do you know how they work, more or less?
Yes, that will be quite a long explanation, I think. But the model that I am working with is called the TISC. And we use this model both for the isostatic calculations and for the surface evolution modeling. So TISC, it stands for tectonics, isostasy, surface, and climate, or surface processes and climate. And the way that it can help to calculate the surface evolution is that it's based on just a grid finite element program that in each cell calculates how much water is being entered into the cell by precipitation, for example, and then calculates the river network. And the amount that it is eroding the material in the surface is calculated based on the erodibility and a lot of other factors that have to do with, but there are different models for how erosion happens, and you can use different approaches. So it's not, there's a lot of uncertainty there. Let's just say it this way. You cannot point to one model and say this is the correct one, but it can give you ideas on how the evolution of a certain basin can happen.
Okay. I get it. Thank you. You want to say something, Lucia?
Yeah, I have a question for Hanneke. Thank you very much for the presentation. It was very nice. A lot of interesting stuff that we normally don't speak about here at Timne. But I'm curious from the modeling side, what kind of software do you use? Are there like commercial software that you can use to do this type of topological reconstruction or not?
Commercial softwares do exist, but the software that I'm using is written by my supervisor, and it's open for everybody to use, and it's free. But of course, oil companies, for example, they also are interested in similar type of things, right, in the evolution of basins. So there are commercial softwares that are able to do similar things, sometimes in higher detail on seismic data, for example. But there are a lot of different options that you can use for this. I can send you a few examples if you want.
I'm curious. What's the name of the code you're using? The one.
So it's called DISC.
DISC. Okay.
Yeah.
Okay. Thank you.
I can put a link somewhere, but yeah, I can show you because it's quite easy to get started with, and it has a lot of options in the end for different types of applications.
Well, you never know. You never know how we are going to bridge towards, and sometimes we might use other codes.
Yeah, true.
I think there was somebody who raised their hand. Yes.
Yeah, go ahead, Marianne. Thank you.
Hi. Not sure if relatives are supposed to ask questions, but I have a very general question. You said at some point that you haven't really figured out yet whether the water level actually dropped very low or if it was always sort of high-ish because of some other reason. So, and then in the rest of your talk, you only mentioned this sort of this deep drop. So does that mean that you've actually proved now that that was the case, or? And if that's not the case, how do you explain these very deep erosion, like these very deep riverbeds, if the water level was actually that high?
Okay, so this is very good question. Now, the way that I am using my models, we are not able to prove or disprove whether the water level was that low, but we need to make an assumption based on geological evidence that we have. But we make an interpretation that the limits, for example, of the halite that we see, that it represents a shoreline, and we make an interpretation that the erosion surface that we see was caused by subaerial exposure. But there are other people that propose alternative mechanisms for the formation of the same observations. So for example, you also see nowadays that you have submarine channels that don't look that different from a channel formed by a river, or people that have proposed that the formation of salt dense water moving down into the deep basin could cause erosion on the bottom. And in the end, it really depends on the perspective that you take, whether you believe in the evidence that we show or not. And in the paper, we also show an alternative scenario where we actually don't have any drawdown, and we show the topography and the water level that we would have in that case. But personally, I believe in the drawdown, which is, well, I think at this point, the majority of people working on the Messinian, they believe that at some point there was a drawdown, but the main controversy is also in how long it lasted and when, and if it was one event or multiple.
Thanks.
I think that Sergio Slotnik raised his hand.
Yes.
Hi.
Hello. Thanks, Hanneke. Very nice talk on a very interesting topic. I have some questions, but maybe you already said that and I miss it. It's about the geochemical data that is available. I don't know if there is much or not data on the composition of the salts, and if it is homogeneous in space laterally, and if if you can grab some information from I don't know, vertical inhomogeneities in the chemistry or just horizontal.
Yeah, no, this is a very good question, and this is part of the problem of not having drill cores that penetrate the salts available for science use. So we have some cores that penetrate a very thick layer of salts from Sicily, for example, but in the deep basin, we really don't know that much about the composition of the salt. But we see, for example, that in the Eastern Mediterranean, internally, it looks a little bit different from in the Western Mediterranean, and it has more internal reflectors. So there might be different things going on there, different cyclical variations in how the halite was formed. And for example, something that is quite interesting is that there is a clear chemical difference between the gypsum formed in earlier stages of the Messinian and gypsum formed in the later stages, where there are people that suggest that the upper gypsum, the gypsum that was formed after the halite, was actually formed in relatively low salinity waters. And they get this information also from water that is preserved within the gypsum crystals. So there are definitely geochemical variations going on within this thing, but part of it is just a lack of data because we don't have the samples available.
In this kind of models, always having some constraints for the numerical part is very difficult. I mean, just to have what are the boundaries that we need to fulfill with our models, and this is usually difficult. So I was guessing that maybe this if you have some layering or some change can help you to determine which one of your numerical models are more accurate or closer to or more probable than others.
Yeah, it's difficult. There is something interesting that we see, for example, in the salt mine in Sicily, where we do have this very thick salt layer that is almost at the surface and it's accessible. And there you see that there are internal, what they think are annual variations in the composition of the salts. And there is also a layer where you have all of a sudden these very, very high salinity salts, and then an unconformity between the salt below and the salt above, which suggests that maybe the salt was exposed to the air somewhere in the middle of its formation. And we don't know if that's representative again for the whole basin. So you have to make some assumptions, definitely, when you're working on the basin-wide scale.
Thank you. Thank you very much.
Thanks.
I think also Miguel Angel raised a hand.
Yeah, very interesting talk. I just was wondering whether there's kind of an overlap between your interests and the oil companies' interests, because I know that they are usually, I'm talking worldwide, not about the Mediterranean. I don't have any knowledge about their activities in the Mediterranean Sea. But isn't there kind of an overlap or a common interest there with oil companies? Because they do a lot of drilling, but maybe not here. I don't know.
No, oil companies are definitely interested because of this hydrocarbon potential that the salt layer represents. Now, in the Eastern Mediterranean, there are known hydrocarbon reserves related to the Messinian salts. But usually those drillings are not just available to or open for, especially when they are related to production interest, they are not open for scientists to just publish. But we do have a collaboration, for example, with an Italian oil company, Eni, and there hopefully we'll be able to share a little bit of the data they have, because they definitely have more than is available to the scientific community at this stage, which probably would help a lot in resolving some of these questions.
Okay. Thank you.
Thanks.
Okay, this is the last call for questions. Any of you want to? Okay, so then let's close this session. Thank you again, Hanneke. It has been a pleasure. I'm going to stop the recording.